Let's talk about the approximation to electronegativity. Hopefully by now you are wrapping your head around the idea that the electronegativity tells you the extent by which an atom can attract electrons towards itself. And the values, as you saw in the table, the periodic table that I showed earlier in the previous video, they range from 0 to 4, roughly speaking. Now what we're going to do is come up with an approximation that roughly gets you similar values to the ones that you saw in the table. And the idea is derived from the fact that there is a Coulombic force of attraction that is based on the charge of the electron square times the effective nuclear charge divided by the radius square. And using that premise, Allred and Rochow came up with a definition, or rather a description of the electronegativity in terms of just the effective nuclear charge divided by the square of the atomic radius. And the formula that's shown right here gives you values that are relatively good in comparison to the Pauling electronegativity values. As the formula 0.359 multiplied by effective nuclear charge minus 0.35, all divided by the square of the atomic radius, all of that added to 0.74 gives you roughly numbers that are, workable. This is the Allred-Rochow electronegativity. Now, in some cases, I may give you questions where I don't provide you with the atomic number of the element, or excuse me, the atomic radius of the element. And in those instances, it will be implied that you have to approximate the atomic radius of the element using this later approximation to the Bohr radius. And then using that number to calculate electronegativity. Now, needless to say, the values you're going to get are not going to be very good. Like the electronegativity values are already a little bit off from the true Pauling electronegativity numbers using the correct laboratory and experimental values of atomic radius. So using approximation on top of this other approximation creates a little bit of error. But interestingly enough, the trends themselves kind of remain intact, something that we saw taking place also with the ionic and atomic radii. And for these approximations, once again, if you have to approximate the atomic radius, you will have to use the effective principal quantum number based on the table up here. All right, now to give you an idea, the periodic table here is showing the electronegativity values for the Pauling scale, which are all in black. These are the ones that you typically see in most any chemistry textbook. And as I was depicting before, they range from about 0 or 0.5 all the way up to about 4. And that's roughly where all the numbers fall. The Allred-Rochow values, using the experimental values for the atomic radii, are kind of similar to the ones that we see for the Pauling electronegativity, although we kind of deviate a little bit. Now we're going a little bit farther than 4 for the scale, but they're kind of close. Now the ones that you have to be, somewhat aware of, maybe really not working all that well in terms of the approximation, are the elements here on the bottom row of the table. Heavy metals like mercury or platinum. Those are actually pretty bad in terms of the approximation. The approximation tells you the values are like somewhere in the mid 1.5, 1.4. When in reality the electronegativity values, experimental ones, are higher by a whole value, so like 2.2, 2.5. The reason that's happening is that for these elements there is relativistic effects that actually do play a role in how well they attract electrons. It's actually kind of interesting to see that for the transition metals you have an increase in electronegativity as you go down the series, whereas for the regular non-metals or the regular main group metals like the alkali metals or the alkaliner metals, going down the series decreases electronegativity. That is not true for the transition metals because there is a relativistic effect that we don't account for, at least at this point in the studies of chemistry. Now that being said, we're gonna kind of take a look at this approximation to to see how we can look at trends in particular. The values we're going to get are not super accurate, but the trend for the given elements is actually maintained relatively well. So let's take a look. We're going to try to arrange the following atoms in increasing order of electronegativity, not atomic radius, but rather electronegativity. And we're looking at boron, nitrogen, gallium, and arsenic. Okay, arranging them in the periodic table, we have boron appearing before nitrogen, gallium underneath boron, and arsenic appearing after gallium and right underneath nitrogen. So based on the regular periodic trends, we expect the electronegativity to increase going up a column and going from left to right. So we would expect nitrogen to be the most electronegative element and gallium to be the least. Then the question becomes what happens between boron and arsenic? Which one is more electronegative? Alright, so we'll place gallium as the least electronegative because of the trend in the series. It's the one farthest down and to the left. And nitrogen is the one with the highest value because it's farthest up and to the right. But let's calculate the values for all four of them nonetheless. We start with electron configurations. 1s2, 2s2p3 for boron, 1s2, 2s2p5 for nitrogen. For gallium we have 1s2, 2s2p8, 3s3p8, 3d10, and 4s4p1. For arsenic we have 1s2, 2s2p8, 3s3p8, 3d10, and 4s4p3. Okay, so you should be able to arrive at this grouping of electrons via Slater's rules by applying electron configuration knowledge that you have acquired in the previous lectures. If you're still having trouble with this, make sure to ask me these type of questions during office hours. But it will be definitely necessary that you know how to write electron configurations and derive the order by using Slater's rules. And speaking of that, we're going to go and calculate the shielding constant for each one of these elements: boron, nitrogen, gallium, and arsenic. And we use the rules right here. If the valence electrons are sp electrons, we stick with the left column. If the electrons are d or f electrons, we stick with the second column. Now in all of the cases here, the rightmost group are sp, 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 and sp. So we're going to stick with the sp column the entire way through. Okay, so in the case of boron, we have 3 electrons in the last group, so 2 of them shield with 0.35 units. After that, we have 2 electrons to the left, which shield with a 0.85 unit. And for nitrogen, out of the 5, 4 of them shield with 0.35. The 2 to the left shield with a factor of 0.85. For gallium, since the 4s4p has only 1 electron, it will not shield itself, so there's no shielding in the same group. But if we look at the group to the left, we have to look at all of the principal quantum number 3 groups, so the 3s3p and the 3d collectively. So we have actually 18 electrons in the group to the left, which shield with a value of 0.85. And after that, we have 10 electrons that are farther to the left, which shield completely. Arsenic, a similar story, but now we have 3 electrons in the last group, so 2 of them shield with a constant of 0.35. The group to the left, which is the energy level 3 groups, has 18 electrons collectively, which shield with a constant of 0.85. And the 10 still further to the left shield completely. So when you calculate the values of the shielding constants, you find out that boron has a shielding constant of 2.40, nitrogen has a shielding constant of 3.10, gallium has a shielding constant of 25.30, and arsenic has a shielding constant of 26.00. Subtracting each one of these shielding constants from the atomic number of the element, so 5 for boron, 7 for nitrogen, 31 for gallium, and 33 for arsenic. Upon subtracting the shielding constants, we get the following effective nuclear charges: 2.60 for boron, 3.90 for nitrogen, 5.70 for gallium, and 7.00 for arsenic. Okay, now we get to use the Bohr radius approximation, including the effective nuclear charge and the effective principal quantum number. Alright, so we're dealing with principal quantum numbers of 2 and 4. Okay, so for the ones that have principal quantum numbers of 2, we need to make sure to use 2 for n star. And for the ones that have principal quantum number of 4, the value of n star needs to be 3.7. So we input that in the equation. We multiply 0.529, multiply by the effective principal quantum number square, so 2 for boron and nitrogen, 3.7 for gallium and arsenic. And then we divide by the corresponding effective nuclear charge. Upon carrying out the calculation, we find out that the atomic radius of boron is 0.814, that of nitrogen is 0.543, the atomic radius of gallium is 1.27, and that of arsenic is 1.03. Lastly, we calculate the electronegativities of the elements now that we have the effective nuclear charge and the atomic radius. So we use the Allen-Rochow formula. We multiply 0.359 by the effective nuclear charge of boron minus 0.35. Same thing goes for nitrogen. And after that, we divide it by the radius of boron or the radius of nitrogen square. Upon carrying out this calculation, which I would recommend first doing the subtraction, 2.60 minus 0.35 multiplied by 0.350, pressing enter, dividing that by 0.814 square, pressing enter, this is for boron, and then adding 0.74 to the equation. This yields a value of 1.96 for boron and 5.06 for nitrogen. Performing the same calculation for gallium and arsenic, we multiply 0.359 by the effective nuclear charge of gallium or arsenic minus 0.35. To that, we divide the corresponding radius of gallium, which is 1.27 angstroms, or 1.03 angstroms for arsenic. We make sure to square those particular atomic radii, and then we add 0.74 at the end. And we find out that the values are 1.93 for gallium and 2.99 for arsenic. So what this basically says is that nitrogen is indeed the most electronegative element out of the 4, and the least electronegative is indeed gallium. The one that is second least electronegative happens to be boron. So boron is the next one in the series, and arsenic actually ends up being more electronegative than boron. So these are things that you wouldn't necessarily get just by doing your typical going up the column and to the left or to the right. But applying the approximations translator gives us a really good way of approximating these values. Okay, on the next video, I'll finish up by talking about the Mulliken version of electronegativity.